Hello students, so let us start our today's class. Today we will talk about ionization enthalpy. Okay, so we have already given an overview over the ionization enthalpy. So today we will move more deep into it, and let's see what are the trends that are observed in the case of ionization enthalpy. So we will see for the first, second and third all type of ionization enthalpies, right? So first, the general trend that is being always seen, okay, almost always seen, is if we move from left to right, is that we see a decrease. Okay, we see an increase in the what ionization enthalpy as we move from left to right. So this is the general trend. Why? The reason is obvious, because the atomic radii is decreasing, so electrons are more close to the nucleus, and hence we have to provide more energy to remove that electron. So this is the general trend that is seen. Now the variation in case of d transition elements, or I would say the d block elements, the variation in case of say d block element for the ionization enthalpy is not that much pronounced as was in the case of non-transition element. So it means that if you just compare two successive ionization enthalpy of two different elements that are on the same period, you will see that the difference between those two successive elements, the difference in ionization enthalpy between those two successive elements is not that much. But on the other hand, if you compare it with the difference between the ionization of the two elements which are just next to each other in the vertical sense, then you will see that there is a change in ionization enthalpy. Clear? Got it? Okay. Now we will move individually to each and every ionization enthalpy, that is first ionization enthalpy, second ionization enthalpy and third ionization enthalpy, and see what the trend looks like. Clear? Okay. Now first talking about the first ionization enthalpy. So here is the graph for all of those three. You can see that as we move from left to right, there is an increase in ionization enthalpy. Normally it increases, then there is an exception, so we'll talk about those exceptions also. But the trend is almost good for 4D and 5D. It is increasing, you can see. But for 3D, you can see that this trend is not that much obvious, but instead it is very changing from here to there, right? So first it's decreasing, then it is increasing, again increasing, then decreasing, then again decreasing, and then increasing. If you compare it with this one, it is increasing. So one element goes up and again it goes down. Here also it almost remains constant, then again increases. Then for one metal it goes up and then we got on increasing. So there is an exception here and an exception here. But in the case of say here, there is a huge exception. So first it increases, then it decreases for 3 metal. Clear? And the answer is the reorganization of electron. So when we take out an electron, some energy is used up. But as soon as this electron is taken out, the remaining electron reorganizes. Accordingly, they move from one orbital to another, so that in that process the energy of the system can be reduced. Clear? Now how it can be reduced? By releasing some energy. So we are giving some energy and some energy is being released after stabilization. Now the net energy is the ionization enthalpy. Clear? And that ionization enthalpy, that change in say configuration due to reorganization results in a you can say a different type of trend for the transition element, especially for the 3D series. Clear? Okay, now let us talk about the 4D series. So it is increasing normally. First for zirconium it is high, then it is decreased, then it is increasing. For palladium it goes up very high. What is the reason behind it? The reason behind it is that as we remove one electron, we have to remove it from the D10, a completely filled d orbital. If you remember, it has electronic configuration of 4d10 5s0. Now 4d10 and 5s0. So if you have to remove an electron, you have to remove it from the d orbital, right? Now again silver falls down. Why is it so? Because silver as soon as we remove electron from silver, then it gains a D10 configuration. What it gains? It gains a D10 configuration, and for that reason we see a dip here. Okay, similar is the case of platinum also. If you look at the platinum, then you will see that there is a dip again there. So this is the reason behind it. Why? Because as soon as we remove electron, it acquires a pseudo noble gas configuration, both for platinum and silver. Okay, both for Au and silver. Clear? Got it? Next. So the irregular trend in the first ionization enthalpy of the metal of the 3D series is though of little significance because the differentiation is not that much, although it is visible in the graph. But if you look at the absolute values, then their difference is not that much, so it is not of that much chemical significance, right? But still, it happens due to the relative energy, change in the relative energy of 4s and 3d, which is of course due to the rearrangement of electron. When d oblong elements forms ion, ns electrons are lost before n minus tn1 electron. So this is a very important point. So although you feel the d electron at last, so whenever you remove an electron, the ns electron are removed first. Okay, so you don't have to remove the electron which is on a higher energy. Instead, you will remove electron which is on a lower energy, which is ns. Okay, ns orbital. Now, when we move along the period in 3D series, the nuclear charge increases from scandium to titanium, but the electrons are added to the orbiter of the inner shell. Now, the 3D electron shields the 4s electron from increasing and from the increasing nuclear charge somewhat more effectively than the outer shell can shield one another. Therefore, the atomic radii decreases rapidly. Thus, the ionization energy increases only slightly after 3D series. The doubly or more highly charged have DN configuration with no 4s electron. Here, so these are some general points. You can just look over it. I've already explained the reason behind that, say, trend. Clear? Okay. A general trend of increasing. Now we will talk about second ionization enthalpy. So till now we are talking about the first ionization enthalpy. Now we will talk about the second ionization enthalpy. So the trend in second ionization and third ionization enthalpy is very simple. It will decrease. There is no exceptions except magnesium 2 plus and Fe3 plus, right? So except these two, we don't have any exception. So as we move from Mn plus to Mn2 plus, we will see an exception. We will see a change in the second ionization enthalpy, and as we move from Fe2 plus to Fe3 plus, we will again see a change or a exception in the ionization enthalpy. So for second and third ionization enthalpy, if you are removing the second electron and third electron, the trend is almost what? The trend is almost steady, except the conversion that is say attributed by Mn plus to Mn2 plus and Fe2 plus to Fe3 plus. Clear? Now, why is it so? Now, for that, you have to look at the electronic configuration. So, if you look at the electronic configuration, you will find that both have D5 configuration. Okay, the Mn plus and the Fe2 plus both have a D5 configuration. And due to the presence of D5 configuration, it is difficult to remove the electron. Similar breaks occur at the corresponding element in the latter transition series also. The three terms responsible for the value of ionization enthalpy are attraction between the electron towards nucleus, repulsion towards between the electrons, and the exchange energy. So these are the three factors. Okay, so the initial two factors are responsible for the irregular trend of the first ionization enthalpy, and the latter reason, which is exchange energy, it is responsible for the anomaly that is found in our, say, what, second and third ionization enthalpy. Clear it is? Sorry, is it clear? Now here is some information about the exchange energy. So although you know it, but it is explained that that due to the delocalization of electron, or the electrons can move easily or can exchange their position. For that reason, the half-filled orbital are kind of more stable, right? So they have greater number of exchange that is possible. So if you talk about D5, then they can change, one electron can change with other 4 electrons, right? For that reason, you can see that this is a kind of delocalization also only, but we are not saying it delocalization. Instead, we are saying it as exchange energy. Okay, so you can say that in this way also, that delocalization is nothing but a complex form of exchange energy, right? Okay, when several electrons occupy a set of degenerate orbital, the lowest energy state corresponds to the maximum possible extent of single occupation of orbital and parallel spins. Clear? Now, Mn plus has 3d 5 and 4s1. So as we move from Mn plus to Mn2 plus, we will get 3d 5. So it will require less ionization enthalpy. Similarly, if you move from Fe2 plus, it has d6. So as we move from Fe2 plus to Fe3 plus, we move from d6 to d5. Clear? So for that two reasons, we see a irregular trend in Fe2 plus and Mn plus. Clear? And again, Cr, if you talk about Cr plus, it is d5 configuration. It will require, we will have to give more energy to remove the electron. So the ionization enthalpy of Fe2 plus is lower than Fe2 plus. In other words, we can say that the third ionization enthalpy of iron is lower than manganese. So the lowest common oxidation states of this metal is +2. So this is very, very, very important that we don't see a +1 oxidation state for the transition element. Okay, we see either +2, +5, +3. We see these, okay, greater than +2. We will never see it as +1. So +2 is the what? It is the lowest oxidation state possible. Now, to form the M2 plus ion from the gaseous atom, the sum of the first and second ionization enthalpy is required. So this is obvious. So what is the meaning of second ionization enthalpy? It is the total energy that is required from moving from an isolated gaseous atom, that is M, to M2 plus. It is not the energy that is required from moving from M plus to M2 plus. It is the energy required for moving from M to M2 plus. Clear? And this energy is in addition to the enthalpy of atomization. So if you want to ionize a metal, okay, if you make ions from a metal, the first you have to change the metal to its gaseous state, right? After making it or making the gaseous state, you have to what? You have to remove electrons one by one to make it to M2 plus. Now the dominant term is the second ionization enthalpy, which shows unusually high values for chromium and copper, where M plus ions have D5 and D10. So this thing is again repeated here. Now the value of Zn is correspondingly low, as the ionization causes the removal of one 4s electron, which results in the form of stable D10 configuration. So what it is written? So as soon as we remove one electron, for the, if you're talking about second ionization enthalpy, so first we remove electron from the zinc, that will result in what? 4d10, okay, sorry, 3d10 and 4s1. Now if you remove one more electron, that will result in a completely filled d orbital, and for that reason the ionization enthalpy is low. Okay, so we are just seeing the same things here, same thing here also. Now let us look at the configuration as a whole. Okay, let us look at the configuration as a whole. Here is the value of enthalpy of ionization enthalpy. Okay, value of enthalpy of ionization. So you can see 631, 656. Again, it's decreasing, increasing. It increases drastically. Again, increases. Then decreases. Then again decreases. Again increases, and at last it decreases very fastly. So this trend is almost non-predictable due to the reorganization of the d electrons, right? But if you talk about the second ionization enthalpy, you can see that it increases continuously. But here only we can see a decrease because of the stability that is obtained by removing one electron from the M plus. Similarly, again it starts increasing. Okay, it starts increasing. Okay, then we see a general increase. Similarly, for the third ionization enthalpy, first is increases. Okay, it increases up till here. Then again we see a decrease, and the reason is very obvious, as we move from 3d6 to 3d5. So M2 plus means you can say that Fe2 plus has 3d6 and Fe3 plus has 3d5. So as we move from Fe2 plus to Fe3 plus, we are moving from a partially filled to a half filled orbital, and therefore the ionization enthalpy is less. Then again it start increasing and it increases up till zinc. Clear? Now if you look at the atomic radii, this is also having a decrease. Almost there is a decrease, but there are some exceptions to it. Okay, now next, now we will talk about the oxidation states. Okay, so if you talk about the D block element, they show a variety of oxidation state, and I have already mentioned the reason behind the variety of oxidation state, and that is very obvious, which is the availability of electrons to be easily removed. Okay, so this is the reason behind the variable oxidation state in one line. Now if you look at the trend here, let us move at the trend directly. So this is the trend, right? If you see in the middle, maximum number of electrons are there that can be removed, okay, in the middle side. Where on the extreme ends you would see very easily, it is visually visible that on the left and right side the number of oxidation state decreases. For the left side, the reason is very obvious, because the number of electrons that is available is low. That is the simple reason behind the less number of oxidation state for the left side, okay, for the D block elements. But if you move to the right side, what is the reason? So the reason is that as we are moving from left to right, what we are doing, we are decreasing the atomic size. Now as the atomic size decreases, the effective nuclear charge on the outer electron increases, and we find it difficult to remove the electrons, and for that reason we see the trend of less number of oxidation state on the right side. Okay, so if you just go back, you will see the same thing written. The lesser number of oxidation state at extreme end, from too few electron to lose, or too many d electrons for higher valence. Clear? Now if you talk about the transition metal, we don't see such trends, right? We don't see that they have a variable oxidation state. It is only seen for the D block elements. Okay, and what is the reason behind it? Because the D block elements have d orbitals involved. So although in the P block the lower oxidation state are favored by the heavier member, the opposite is true for the D block element. What it is written? That the P block element lower oxidation states are favorable by heavier members, right? But in case of the D block, the higher oxidation states are stabilized by the P block element or the transition metals. Okay, for example, the molybdenum 6 and the tungsten 6 are found to be stable than chromium 6. That chromium 6 in the form of dichromate in acidic medium is a strong oxidizing agent, whereas MO3 and WO3 are not. Okay, so low oxidation state are found when a complex has ligand capable of pi acceptor, therefore in addition to the sigma bonding. So what it is written, so if you have to see the low oxidation state, then the ligand should also be pi acceptor. So in coordination element you will see that ligand will donate electron to the metal, as well as ligands will accept electron from the metal, right? So this is very unique, and that effect is called synergic effect. Okay, that effect is called synergic effect, in which the metal is also what? It is giving electrons. For example, you will see it in the case of nickel carbonyls and iron carbonyls. Clear? Now, which of the 3D series of the transition metal exhibit largest number of oxidation states and why? So you have seen this. So the reason is that they are relatively close to the nucleus and are therefore more easily lost or gained. Therefore, this allowed the transition metal to show the variable number of oxidation state. Now let us move to standard potential. So the unique behavior of copper having a positive E0 account for the inability to liberate H2 from acid. So if you just look at the say standard potential E0 cell, you will find that the copper is the only one that is capable of what? That is having a higher reduction value. So it will be capable of getting reduced, and it will be the only one that is capable of oxidizing hydrogen. Rest all have a negative value. Okay, rest all have a negative value, which means it has a lower value than hydrogen. Clear? So this is the trend. You can see that all have, sorry, copper is the one only which is having the positive value. Okay, I have told that. So here you can see very clearly that for copper only, this value goes above the 0, which means that copper is capable of oxidizing hydrogen, and it is the only one. Rest of all are having a reduction potential smaller than 0. So this is obvious from this graph. Now, if you talk about the general trend towards less negative E0 value across the series relates to the general increase in the sum of first and second ionization enthalpy. It is interesting to note that the value of E0 for Mn, Ni and zinc are more negative than expected from the trend. Okay. Now, why is Cr2 plus reducing and Mn3 plus oxidizing when both have D4 configuration? So it is due to the splitting of d orbitals, right? Because it is due to the splitting of d orbital. So this you will study about this more accurately in the coordination compound, but for now Cr2 plus is reducing because its configuration is changing from D4 to D3. The latter is having half filled T2G orbital. On the other hand, if we move from Mn3 plus to M2 plus, so it results in the half filled. Okay, the stability of the half filled subshell in Mn2 plus and the completely filled D10 configuration in Zn2 plus relate to their E0 values. Now, if you talk about the M3 plus and M2 plus E0 values, the low value of scandium reflects the stability of Sc3 plus. So it has a very low value of scandium, which is due to the because it attends the noble gas configuration, right? The high value of Zn is due to removal of an electron from the D10 configuration, and the relatively high value of Mn shows that D5 is particularly stable. So this is all about D5 and D10. Similarly, Fe3 plus will show extra stability due to attending, because it is attending D5 configuration. Similarly, the relatively low value of relates to the stability of V2 plus, which is half filled T2G level. Now, high oxidation state achieved in TiX4. So we will talk about which oxidation state is stabilized by which anions. So higher oxidation state is generally stabilized by more electronegative elements. So fluorine is the one, but there is an exception. You can see that this is the normal thing. You will see that higher oxidation state. Here you can see that Cr plus 6 oxidized by stabilized by fluorine, but oxygen is more capable of doing so. Why is it so? Because vanadium plus 5 only represent V5, but other ligands undergo hydrolysis to give VOX3. Fluorides are unstable in low oxidation state. So this I have told, because they are stable in the higher oxidation state. Now oxides have a greater tendency to form higher oxidation state metal as compared to fluorine. So here is the trend for that. Okay. Because why is it so? Because they have a property to form multiple bonds, which is not seen in the case of what? Fluorine. It forms only one bond. So here's a question for you. You can do it by yourself. It's an easy question. So this was for today's class. Thank you.